Welcome to what's apparently the first Saturday Morning Physics. And I want to thank the organizers of Saturday Morning Physics. I'd really like to thank, too, the organizers of Michigan in Climate Crisis that has provided a great week of thought-provoking talks and discussions and seminars. And I want to thank all of you for showing up, taking some time out of your Saturday morning. I'm going to tell you two things, some things that we know and some things that we don't know about climate change and the Arctic. So starting in the 1800s, people understood the effect of greenhouse gases in warming the atmosphere. Around 1900, the first scientific prediction of Earth's warming due to industrial activities putting out CO2 was made. In the 70s, we had the first models, global models, showing that the Earth was actually warming rather than going into another ice age, which is what I was taught as an undergrad, which takes us up to today, where despite 115 years since the first scientific prediction of this warming, we're still trying to convince people of financial and political power that this is not simply a blip, a random blip in Earth's history. And we have a lot of information about CO2 now in the atmosphere, what's driving these changes. This is a graph showing this is a graph. I'm going backwards in time. Let's go forward in time. This is a graph showing the CO2 concentrations in the atmosphere from the Mauna Loa Observatory here in Hawaii. And you see that there's this cyclical change in CO2 in the atmosphere. The CO2 goes down when essentially the plants of the northern hemisphere during the summer are breathing in CO2 to use in photosynthesis. And the graph goes up when those plants in the wintertime are respiring, as well as the microbes and other organisms in the soil are respiring. And so this defines really the Earth's effect. The amplitude of this change is what the Earth is doing over time with its exchange of CO2 with the atmosphere, with the oceans, and with land. Now, the next thing you notice about this, of course, is that there is a strong upward trend. This upward trend is the human effect. This is what we're doing. And you can see right away that this human effect dominates over natural variations in CO2. So many climate deniers, for example, will pick out small little bumps in the CO2 record, and they'll ask, how do you explain this? What's really going on in the model that explains that little thing? Climate scientists, on the other hand, are saying, well, how do you explain this? This is the change that is due to humans. So we know that we can explain this now. And this is a simulation, a 5-day simulation of CO2 sources from megacities. And those are the little blue puffs that you see coming out here from Southeast Asia and in the US. That's the CO2 from megacities and biomass burning here, most often in the tropics. So we see these changes and we see the sources of this, and we know where to point our finger, and we also see the impacts of this. So this has changed the Earth enough so that we've seen major differences, major shifts in things like Arctic sea ice. Arctic sea ice has been melting since the 70s, when we had really good records up to 2016. We have lost a tremendous amount of this sea ice due to global warming. We also have, at the same time, changed the albedo of the Earth. We're now absorbing more solar radiation than we were in the past because of this lost ice from 79 in the upper right down to 2012 here. And as I say, we know that this is affecting not only the sea ice, but glaciers. These are Alaskan glaciers, where you see changes here in the Peterson Glacier, in the Muir Glacier over time. And one of the most striking changes in only 25 years is here at the Columbia Glacier, where you see this great recession of the glacier front back here in 2011 compared to just 1986. So we know who to point the finger at for these kinds of changes. That's not a difficult thing to figure out. And because we can measure the outputs of CO2, especially from human activities, we can make predictions of this into the future. And these predictions, then, look something like this. So this is a reconstruction using a climate model that scientists are using together. This scenario here, if you're interested, is the business as usual scenario. And we see that by the end of the century, we have quite a bit of warming. 20 degrees Fahrenheit warming in Arctic regions. Now, I'll tell you one more thing about these kinds of models and other models that scientists have that look at sea level change, for example, and glacier melting. We know they are all wrong. They're all wrong because they're underestimates. Almost every model that we've built, when we look back at the record, it fails to predict it, the actual record, because we've underestimated the strength of the change. And I know for a fact that this same problem is occurring here in this model, is predicting into the future. And the main reason it's occurring is because of the Arctic. So we're pointing a finger at the Arctic. Can the Arctic be both a victim and a culprit in this? The Arctic has not been included in these models because we don't understand how the warming in the Arctic will affect the permafrost soils. So in the Arctic, there's a tremendous amount of carbon stored, frozen below ground, has been frozen for a long time. And we don't yet know what kind of a tipping point will be reached and how fast those soils will thaw and contribute to climate warming. So that's what I want to talk about a little bit here. This is the permafrost. Permafrost is simply permanently frozen soils. Actually, permanently is a little bit of a misnomer. It has to be frozen for 2 years running to be called permafrost. The engineers came up with that explanation or definition. But the fact is that in these pink areas here around the north, so this is just a view from the North Pole of the globe. These pink areas are continuous and discontinuous permafrost, which contain tremendous stores of carbon. We're now reaching the point where this kind of a major biome in the world is going to shift its behavior, and it is starting to thaw. So the soils are thawing, potentially contributing a tremendous amount of carbon to the atmosphere. So I need to go through a couple of things with you. So this is like opening the tomb of this long frozen, thousands of years. This carbon has been frozen, not participating in the modern global carbon cycle. Now it's going to start. So this is what these soils look like. At the surface in Arctic, you have a layer that thaws every summer, only about 1 or 2 feet deep. That's as far down as it goes. And beneath that, we have this permafrost layer, these permanently frozen soils that can extend tens and even hundreds of meters down into the earth. And this is where all this carbon is stored that hasn't been in the Arctic carbon cycle or the global carbon cycle before. So I want to talk to you a little bit about, set the stage for this, put some context into this. The biggest pool of active carbon, more or less active, on the Earth is oceans. The largest pool is in rocks, but they turn over very slowly. Turns out the ocean turns over very slowly too. The circulation, the ocean ventilates to the surface and can exchange carbon about every 3,000–4,000 years. This is the amount of carbon that we have in the atmosphere here. And the atmosphere and the ocean exchange a little bit of carbon. There's a small net uptake of carbon by the oceans every year. The atmosphere is increasing at 4 gigatons of carbon per year here. And then we also have this major land pool. About 3 times as much carbon is stored in this land pool, plants and soils. But fully 2/3 of that carbon is stored in these permafrost soils. Now, this carbon on land runs off here down into lakes. Some of that goes back as CO2 up to the atmosphere. That's a source. The rest of it runs off back into the oceans. We also have that breathing of the planet that we saw earlier, the net of photosynthesis and respiration consuming and producing CO2 is about 3 gigatons per year going into land. Now, the real driver of climate change, though, is this large input, about 9 gigatons per year of fossil fuels and land use changes that are driven by human activities. And this is what has really changed the cycle and moved it toward these tipping points. What we don't know, then, is how much CO2 is going to come from the permafrost. And that is the question, how that added CO2 will amplify climate change and alter the arc of climate change in this next century that at least some of you out there in the audience will see a lot of. So, what's Arctic amplification? It's simply a positive feedback between a warming world and a thawing permafrost. So, we start off with global warming. That leads to more thawing of permafrost soils, which leads to increased CO2 release, which then fuels increased global warming. So this is the positive feedback loop that we have. And the question then becomes, how much of the carbon in the soils will actually be respired to CO2 or converted to CO2? One other thing, we know that what happens in the Arctic doesn't stay there, it goes everywhere. So this is just looking at CO2 concentrations, and what we know is that CO2 mixes within a hemisphere in about a month and across hemispheres in 2 to 3 years. So it's not only about what will happen in the future or what will happen in the Arctic. What happens there will be translated everywhere very quickly. So we can start looking now in more detail about what's going on. We've got, and what the controls are. We've got thawing of permafrost, releasing carbon into surface waters. Then the microbes, the bacteria take over, and they respire that organic carbon to CO2. Once this material comes out into the surface of the Earth, we also have exposure to sunlight. And the sunlight degradation can also take organic carbon and turn that directly into CO2. And I want to just highlight that point. If you have a bag of tea in these little whirl packs, transparent to UV radiation, I bet all of you can predict what will happen if you put one in the light and leave another one in the dark. Right? It's going to be bleached in the light. The tea is bleached over time, and when that carbon is bleached, it's also producing some CO2. So there's a direct production of CO2 just from sunlight. Okay, where do we do some of the work then, asking this question about how reactive this carbon is? We're working here up on the north slope of Alaska, down here in the right at Toolik Lake. There's Alaska, the north slope. This is the all tundra, treeless, the Arctic Ocean up here. This is the camp, Toolik Lake camp here. And you see that there's a lot of green vegetation. There's a lot of carbon around. This is a false color image, and so all of that's red there on the right, it is actually green vegetation. So there's a lot of carbon around. And what we did, and I have to acknowledge that the work was done by Rose Corey and her lab here at the University of Michigan, Byron Crump and his lab at Oregon State, as well as people in my lab. And first thing we did was dig soil pits and to get down to the frozen layers. And you can see that we've sampled here the surface layer carbon, that's the carbon that thaws, the soil that thaws every year, and then this deeper frozen permafrost. And then what we did is expose it or feed it to bacteria and expose it to sunlight to see what happened. And this is what we found. The first result here is that the deep permafrost soils are just as easily respired to CO2 as are the shallow thawed soils. So this is the surface, and this is the deeper permafrost. They may even be a little more reactive. So they're not unreactive. They're not going to just do nothing when they're thawed in terms of bacterial respiration. The second thing we looked at is how much the sunlight will degrade the CO2. And what we see here is that this carbon that's at the surface now and the permafrost carbon have the same sort of lability. They're just as reactive to sunlight. So this is the amount of CO2 that's produced over time. And then there's another interesting thing here, an interaction, a synergistic interaction between the sunlight and the bacteria. Remember in that tea bag picture, not all of that carbon that is changed goes to CO2. Some of it is simply altered, and that alteration actually affects how bacteria then use that carbon. And it turns out that if you expose carbon to light, the bacteria are increased in their activity by 40%. So these plots here show the amount of bacterial activity. This is the bacteria held in the dark. This is the bacteria when they've been fed this organic carbon that's been exposed to light, and consistently there's greater production of CO2 or bacterial activity when there's light in the equation as well. Okay, so the conclusion from this data that we have is that the carbon stored in permafrost will be converted to CO2. It's not highly resistant, and it will accelerate the Arctic amplification. Now, some of you may be asking, but isn't this all happening far into the future? Why do we have to worry about this now? Isn't this happening in the 2050s or 2100s? Well, that doesn't mean that it's not going to be important for the world. But in fact, there's more and more evidence showing that these changes in the Arctic now are affecting our current weather, not only climate into the future. So I want to talk about that a little bit. And what we need to do is think here about something called the jet stream. If you look on Earth here, we have warmer air. Because the warmer air here at lower latitudes rises, it makes sort of a slope here. That air moves down. So air flows down this hill from the warmer lower latitudes to the colder higher latitudes. And as it's flowing down that hill, the Earth is rotating underneath it, and that is turning it, and that is creating the jet stream. Now, as the Arctic warms, this hill flattens, and what happens is that the west winds of the jet stream now become weaker. So why is that important? Why are weaker winds important? First, let's look at the jet stream. This is just a simulation of about a month's worth of jet stream. Here, red is not higher temperature. Red is higher wind speed. And you can see this, this jet stream, the higher wind speeds here that are affecting our climate. You see one of these nice patterns that you see on the Weather Channel here where you have a lower trough and a ridge up here. And you see that this is connected to the poles and to the Arctic, and so this is going to be colder weather. Behind that jet stream, it's going to be warmer weather. And as I mentioned, this is what you see on weather forecasts all the time. So these are the kinds of effects that the jet stream has now, where we have cold, wet, and stormy weather on the front side, warmer weather on the back side. If the jet stream winds weaken, then what happens is that the jet stream itself can move further south. And so we have periods here where the deep cold from the north extends further south. At the same time, if we warm the Arctic, what we have is we strengthen this ridge here, which can actually stall out the jet stream, or make it be stuck. And a stuck jet stream lends itself to having extreme weather events. So these extreme weather events then are illustrated here. When we have a stronger jet stream here on the left side, you see that it's fairly well contained. The winds are very fast, the winds are strong, and we're containing the cold polar and Arctic air up here in the north. However, with a weaker jet stream, the winds are able to move down lower and affect our climate here in the temperate zone, and these systems can then get stuck where we have long periods of rain or long periods of drought that are associated with this weaker jet stream. So, Arctic amplification is not only going to affect our climate in the future, it's affecting our current weather today. And that will only become more extreme. So, these are my conclusions. Future arc of climate change on Earth depends on human emissions of CO2. The CO2 released from thawing soils in the Arctic could and will have an accelerating effect due to this positive feedback loop, and the effect on our weather from this Arctic amplification will continue to increase over time. So that's all I have to say. I want to thank everyone for listening. I'll turn it over to Ivette, but I do want to remind you that as we've heard people talk about this week, this is something that is not just a scientific debate. It really hasn't been a debate for a very long time. We're at the point where we need to take action, and we need leaders to step up to do this. And so one of the things, one of the movements on campus that the students have put together is to get not only our campus, our university, but we should get local and regional governments to commit to the Paris Climate Treaty and to divest from fossil fuels. All right, thanks a lot.
Yeah. But where is the pointer? Yeah. The green. Okay.
Thank you very much. Thank you, George. And I want to echo that call to action that George just made. Okay, so moving on to the tropics. So when we think about the tropics in the context of climate change, oops, doesn't seem to be working. I'm sorry.
I'm sure you'll figure out
okay.
back faster than I did.
So the second one is for, yeah, okay.
Go ahead.
Okay, so I was saying that when we think about the tropics in the context of climate change, these are usually the images that come to mind, no? Deforestation, forest burnings in the Amazon, and cattle ranching, and that's for good reasons. Because land use change, mostly in the tropics, and agriculture contribute 24% of the greenhouse gas emissions. Now, emissions from tropical deforestation come primarily from the burning of the trees and the decomposition of the trees. And these emissions amount to approximately 3 gigatons or 3 billion tons per year. Now, evidence is accumulating that in the tropics, we also can have some amplification going on. And for example, a paper that was published just recently of a study that was done in Borneo found that hydrological droughts from climate change and deforestation are increasing wildfires. And this leads to forest loss, which of course will increase the probability of having more droughts and therefore more wildfires. And in this graph that you see here, you can see the relationship between the area in drought and the area, here the area in drought and the area that burned. And the open circles represent years of drought, and the closed circles represent years that were not in drought. So these hydrological-driven droughts that get also complemented with climatic droughts are leading to this kind of feedback loops. Now, in the Amazon, we're seeing something similar. Reduced rainfall has been shown to increase the risk of forest dieback, and that forest loss might intensify regional droughts, again forming another feedback loop that leads to more greenhouse gas emissions. And in this paper that was published last month, the authors are showing that the risk of self-amplify in the Amazon forest loss increases with in a nonlinear fashion. And the study also suggests that these frequent extreme drought events have potential to destabilize large parts of the Amazon forest. Now, agriculture is a different story. The emissions that are coming from agriculture are primarily in the form of methane that comes from rice production and cattle, and also nitrous oxide from fertilizers in intensive agricultural system, industrial agricultural system. And this is important, of course, because methane is 30 times as potent as CO2, and nitrous oxide is 300 times as potent as CO2. And the estimates are that in these agricultural areas, the emissions are 5.3 billion tons or gigatons of carbon equivalent. Today, almost 50% of the area that can have vegetation have been converted to agriculture. And according to the Global Land Cover database for the year 2000, there are 22.2 million kilometers square of agricultural land in the planet. And these areas continue to expand. And they continue to expand, particularly in the tropics. And indeed, it is estimated that 80% of this expansion is actually replacing tropical forests. Like in this particular example that I'm giving here, oops, sorry. In this particular example that I'm giving here is a soybean plantation in Bolivia, in an area that used to be tropical rainforest. So given that there's this large proportion of the planet that is covered with agriculture, actually, and that is expanding, it is important to know how much carbon is stored in these systems. And after all, plants are made out of carbon, of course, and there's some carbon that is stored in these systems. So estimates from the IPCC put that carbon in approximately 1 billion tons of carbon in above and below ground biomass. But that assumes that most agriculture looks like this. And this is, what people think about when they think about agriculture, especially in developed countries, in industrialized countries. But not agriculture look like that. In fact, plenty of agriculture, especially in the tropics, and the kind of agriculture that is practiced by small-scale farmers look like this. And the difference between this and this are the trees. And of course, trees are made out of carbon, and trees store much more carbon than herbaceous vegetation. So these are agroforestry systems, and these agroforestry systems are systems that combine crops with trees and livestock with trees. And these turn out to be fairly common systems throughout the tropics, in particular the tropics. We're seeing a little bit more of these systems in the temperate zone, but they haven't become very popular yet. Now, these systems have gone under the radar screen of many of the estimates that have been done in terms of the role of carbon storage in agriculture. And in 2010, this is data from 2010 that show that more than 43% of the total agricultural land in the globe has more than 10% tree cover. And so when we do estimates that only assume that there's only herbaceous vegetation there, these are underestimates. This map shows the distribution of tree cover in agricultural land. And as you can see, there is this followed broadly the bioclimatic zones, especially in particular related to aridity. The high tree covers, that is more than 45% of tree cover, is found primarily in the humid regions of Central America, the western and central part of Africa, and in Southeast Asia. Now, how does this translate into carbon storage? Using or combining the geographically and bioclimatically stratified IPC default estimates of carbon and combining that with the tree cover data that I just showed you, Sommer and colleagues estimate that there are more than 45 billion tons of carbon on agricultural lands globally. And trees contribute to 75% of this. So there is a lot of carbon that is being stored in these kinds of agroforestry systems. Here's the global distribution of these 45 billion tons of carbon. And of course, they follow the same distribution as the tree cover. And it comes to an average value of 21.4 tons of carbon per hectare. Now, this is about 4 times as much as had been estimated earlier. And although this amount is very small indeed, in comparison with the amount of carbon that is stored in the soils, including the permafrost that George was talking about, biomass carbon on agricultural land deserves attention for its mitigation and for its mitigation potential and also adaptation benefits for farmers. In addition, trees and agricultural land have direct impact on the livelihoods of hundreds of farmers, especially small-scale farmers in the tropics. I work in coffee agroforestry systems in Mexico and Puerto Rico. And this is a farm in Puerto Rico that we have been studying. And in this farm, for example, you find that the farmer produced coffee, but not only coffee, but all of these other crops that you see there: plantain, bananas, ñame, malanga, yautía, apio, cassava, sweet potato, oranges, grapefruit, bitter orange, mango, pigs, chicken, goats, sheep, cows, guinea fowls, rabbits, and I'm sure that I missed some here, but of course, trees as well. Now, in the system that we study in Mexico, we study the multifunctionality of these systems. So it's not just that you have trees there that are sequestering carbon, but also there are multiple functions that these trees play. And in particular, we study ants, and in general, I am a community ecologist, and I study interactions among different organisms in the coffee farm and the complexity of those interactions. And in the coffee farms in Mexico, we have this ant, Azteca sericiazur, and this is an arboreal ant that nests on the trees and forage. So it nests in the trees and forage on the coffee plants. Now, this ant is a very important predator of the main pest in coffee, which is the coffee berry borer, that little beetle that you see there in the picture. This is a picture by one of my students, Jonathan Morris. And so this ant that is living in the trees, is nesting in the trees, is a very important predator of the coffee berry borer. But that's not the whole story. This ant is attacked by a parasite. It's a parasitic fly that oviposit by the base of the head of the ant. The larva enters the head of the ant, start growing inside the head of the ant, eating the inside of the head capsule of the ant. And when the adult is ready to come out, to emerge, the head falls off and the little fly comes out. And here you can see the head of the ant and the little fly coming out. Now, it turns out that this fly changes the behavior of this ant. And by changing the behavior, the ant gets paralyzed when the phorid is around, when the fly is around. And by changing the behavior, it allows then another species of predator that is very important in the system to persist and reproduce in that system. Because normally the ant will chase away these other predators. But when the phorid is present, then this other predator can oviposit in the coffee plants and can reproduce. And this is a very important predator of another pest of coffee. And so here you have a very complex interaction. I just told you two pieces of the network of interactions. But basically you have, let me go back here. Basically you have this ant, which is a keystone species. It's an important species that if you eliminate that ant, a lot of the other interactions can basically break down. And so this network of interactions have resulted in what we have demonstrated that they play a role in the control of 4 of the major pests in coffee. And of course, when you have coffee systems that get intensified and basically reduce or eliminate their tree cover and move from these systems here to these systems here that have no trees. And here's a picture of one of these monocultural systems in Costa Rica. When you eliminate the trees, you're eliminating this keystone ant species. And by eliminating that keystone ant species, you're breaking down that complex network that is acting to control the pests in coffee, and you can have then the outbreak of all sorts of other pests in the system. Now, another thing that this type of shaded systems in coffee do is that they contribute to the adaptation, as I mentioned before, to climate change, no? And they do that by buffering against microclimatic conditions and also by protecting against extreme weather events that we know are going to be more frequent with climate change. And this is the data from a colleague of mine that did a study after Hurricane Stan in Mexico. This was in 2007, 10 years ago. There was this hurricane that passed by Chiapas, Mexico, and affected the coffee growing region. And you can see here, this is as the systems move from the very shaded system to the monocultural system in this direction here, you see that the percent of the farm area that is affected by landslide increases. Now, this is going to be very important for our project in Puerto Rico. As you all know, Puerto Rico was hit by a devastating hurricane 2 weeks ago. I still have not been able to communicate with some of my colleagues in the central mountainous region in Puerto Rico. I got these pictures from the web. It's the first pictures that are coming out of the central mountainous region in Puerto Rico, the coffee growing region. And these are pictures of coffee that have very little shade cover. Now, we're working in Puerto Rico in coffee farms that range that whole spectrum that I showed you before, from very, very shaded systems that look like forest to monocultures of coffee. And so these systems here that you're seeing, these pictures are systems that are farms that have very little shade cover. when we go back, we're going to measure the ecosystem services in these farms, and we're going to measure the impact of the hurricane, and to see what is the role that the trees played in perhaps protecting the coffee plants from the impact of the hurricane. And I'll report to you back sometime in the future. But of course, we haven't done that study yet. So to finish off, I'm going to go back to the map that I show you, the type of maps that I showed you before of carbon, the biomass of carbon, but this time, this picture is showing the changes in biomass. And the news are not that negative in the sense that there actually been an increase in the amount of carbon on agricultural lands. I want to emphasize that this map includes only the agricultural lands. So every dot that you see here is in the agricultural lands. And what you can see here is that there are areas where, there are areas where the amount of carbon on agricultural lands have been increasing. So these are systems that are moving more toward agroforestry systems. We need to do more detailed studies about each, what is happening here. There's some disturbing areas. For example, you can see here in Argentina, you see more of a decline, and that is almost for sure is due to the expansion of soybean production in this region. This is kind of the main area of soybean production here. So that's likely due to the shift towards soybean production. You see that here in the western tip of Africa, Sierra Leone, there is also a lot of loss of carbon, and we don't know what's happening there. But then we see some areas where we see a lot of increase in Southeast Asia, in some areas in Africa, and Central America, and especially in Brazil. And to conclude, I would just talk about these agroforestry systems as multifunctional systems. I want to remind you that these are multifunctional systems that in addition to produce coffee or whatever the main crops are, the trees that are planted with the crops produce also firewood, produce wood for construction, fruits, shade. They also buffer against microclimatic conditions. They offer prevention against extreme weather events. The biodiversity that is included in this system, which is something that I work a lot on, in my lab work a lot on the biodiversity conservation in these systems. They also offer ecosystem services like pest control and pollination services. And also, they build up soil organic carbon in the long term. But in addition to that, as I mentioned in the earlier part of my talk, they increase the biomass, the carbon biomass. And so they represent a storage, small, but nevertheless a storage of carbon in these systems. So even though this is not the panacea, of course, for climate change, I think that agroforestry should be part of the solution when we're thinking about how to deal with the issue of climate change and how to reduce the amount of carbon dioxide that we have in the atmosphere. And with that, I'm going to thank you all for coming today, and we will open it for any questions that you may have.